For decades, engaged participants in the space industry have been looking to the future, and within that future, to the viability of large-scale human colonies in the near and far reaches of space. Early ideas were science fiction, but engineering and ingenuity have caught up with the ambitious hopes of a spacefaring civilization. Around 2005, an illustration of a domed lunar city 25 miles in diameter and 5,000 feet tall over Shackleton Crater began circulating in briefings at aerospace conferences. At first glance, this domed community seemed structurally impossible. However, materials such as basalt fibers and S-glass, among others, could make this type of structure possible. Pause for a few seconds and support me with a subscribe. The total mass of silica in the concept of this dome is approximately 1.6 x 1010 tons. Completion of the dome in about 15 years would require mining rates on par with helium-3 production, which involve excavation, processing, and manufacturing rates approaching 25,000 tons per hour. For instance, the mining capability for tar sand at a typical facility is about 28,000 tons per hour. Size: 25 miles in diameter, 5,000 feet tall. Main components: dome, anchoring system, maintenance systems, catastrophic repair facility. All assembly is via autonomous robotics. All glass is manufactured in layers to enable thermal stress control. Basic unit is a hexagonal pentagonal surface patch of glass with a titanium frame that interlocks with similar units. Dome is anchored to bedrock. Shield glass module is 2 to 3 meters thick. Internal and external lattice work, along with scaffolding for assembly. Given that we are currently in the midst of a technological revolution, the lunar production rates required to construct a dome are well within reach once space manufacturing is established on the moon. From a purely pragmatic standpoint, the magnitude of any lunar settlement project would necessitate the utilization of autonomous robotics to reduce costs and to ensure both safety and an acceptable timeline for completion. Construction could begin in 20 years and be finished 15 years after that. Dome engineering can be performed by many architecture and engineering firms. The opportunity for innovation at engineering firms doing this kind of work could re-energize science and math education here on Earth. The original city must be created underground. The city will consist of several sections connected by a transportation system of commuter rail lines. As underground infrastructure expands, subscale domes of increasingly larger size will be built and integrated into the system. The dome itself will be a substantial structure and, when complete, will allow for the actual living, recreation, and business quarters for the first lunar settlement. The moon provides an excellent testing ground for space settlement, as well as many opportunities for scientific advancement. Because the moon's atmosphere is a near vacuum, it is useful for science, manufacturing, production, and ballistic transfer. It provides heat sources and sinks, an exotic atmosphere, and volatiles for resource utilization. The regolith contains comminuted basalt and anorthosite, and the terrain is covered with cliffs, valleys, and craters, which can be exploited for energy generation. In addition, the ultra-dry conditions on the moon are supportive of electrostatic effects for material handling and classification. The relatively still surface provides an excellent platform for observatories. Finally, the moon's face is shielded from Earth's electromagnetic noise, providing an uncontaminated location for electromagnetic observatories. A 10,000-person settlement would require an initial 20 to 30 tons of material from Earth to be placed on the lunar surface to begin operations. It is imperative that a lunar settlement use materials already on the moon to ramp up production capability. For each kilogram of material produced from resources already on the moon, more than 61 million joules of energy can be saved. An additional benefit is that the lunar regolith is in fine particle form, with significant surface area, thus eliminating the need for comminution, one of the most expensive costs associated with ore processing. Producing lunar building materials involves both chemical engineering and space manufacturing. The lunar regolith lends itself to engineering and manufacturing by virtue of its major constituents: oxygen, iron, titanium, silicon, magnesium, and aluminum. Silicon can be utilized to create high-strength glass. Titanium, iron, magnesium, and aluminum are valuable components of structural materials. Oxygen can be used in the manufacture of ceramics. Chemical processes that can produce metals, ceramics, glasses, powders, and fibers have already been built and tested. One of the most promising processes is the hydrofluoric acid leach system. Once mill-stock materials become available, it will be necessary to begin building more processing and upgraded manufacturing capability, as well as vehicles and construction equipment. The first vehicles built will be relatively small. However, later vehicles and machinery will include those on the scale of a mining bucket wheel. This base, which will evolve into a city, provides a safe haven during initial development, and during any breach that causes depressurization of the dome. The underground base, therefore, continues to provide protection from damage to the dome structure, even after completion. To protect against catastrophic damage to the domes, apertures comprising 4 times the area of the largest expected breach of the dome will have the capability to port air into atmospheric cryogenic condensers at the speed of sound. This would allow for the recovery of 4/5 of the atmosphere in the event of an irreparable breach. Maintenance and repair machines on both the inside and outside of the dome will deal with the maintenance and replacement of damaged polygons in the dome structure itself. The dome must be designed to prevent the propagation of damage from a surface patch blowout. If breached, the system must repair the blowout and limit the risk to personnel on the ground. Breaks in the dome will be sealed by exterior repair machines which stretch over and seal several cells. Additional repair equipment must be capable of using cables to bridge and patch a break larger than several cells. Major cryogenic condensers at 30 degrees Kelvin situated beneath the dome floor will be capable of condensing some or all of the atmosphere, depending on the nature of the damage and how early it is detected. Emergency personnel systems could transport colonists to the underground city or safe harbors within the dome, all of which will be able to withstand vacuum. Mobile systems will seek out and protect people caught out in the open on the surface, on the dome, or outside the habitat. While the lunar regolith is almost 50% oxygen, the nitrogen composition in the lunar regolith is not enough to build this system without modifications. This issue can be mitigated by building smaller, interconnected domes, or by obtaining nitrogen and other cometary gases from the lunar polar craters. Gases may potentially be found in the regions of Kepler and Aristarchus, as evidenced by the planetary probes and Apollo, which discovered outgassing from the lunar interior via the detection of radon-222 atoms above the surface of the moon. There is no question that a domed city on the moon is technologically viable. The technology development required for this project will directly result from the technology required for large-scale space solar power satellites and helium-3 production. If these precursors are developed, this lunar dome project would be a natural next step. The only question remaining is whether a lunar domed city is politically feasible. Endeavors such as this one require sound technical leadership. Recent examples of such leadership enabling stunning technical successes include Count Ferdinand von Zeppelin, General Leslie Richard Groves, Manhattan Project, Admiral Hyman George Rickover, Nuclear Navy, and General Bernard Adolph Schiever, Air Force, Ballistic Missiles and Derivatives. This kind of leadership will be necessary in order to implement a phased, multi-year development plan to build up the required lunar infrastructure. Once sound leadership is established, project success is merely a matter of addressing and solving material, chemical, and engineering issues. The design of large-scale human colonies on the moon and beyond is no longer a responsibility that lies exclusively with the authors of science fiction. The question is not whether a domed moon base is technologically viable. It is. The question now is, when will the vision be joined by sound leadership? Take a moment and give us a like for this video. Thank you so much. China has executed a record-breaking high-orbit refueling mission, signaling a major leap forward in the lunar space race, and leaving U.S. officials openly alarmed. In a breakthrough that could redefine the strategic race for the moon, China has successfully executed a satellite-to-satellite refueling operation in geosynchronous orbit, according to reporting from the South China Morning Post. The operation involved two of its mysterious spacecraft, Shijian-21 and Shijian-25, and may represent the largest single satellite maneuver ever recorded in that orbit. This technological leap is prompting U.S. space officials to raise alarms, warning that China may now be on track to land astronauts on the moon before the United States. The feat took place in early July 2025, when Shijian-21 and Shijian-25, parked at around 36,000 kilometers above Earth, performed a maneuver that shifted their orbital path with a velocity change of over 330 meters per second. That change is unprecedented for satellites operating at such altitudes. Former Deputy Commander of U.S. Space Command, Lieutenant General John Shaw, described the move during a Senate hearing saying, "That's actually a lot, at least by today's standards." This level of velocity adjustment is massive in geosynchronous orbit, where satellites typically use minimal thrust to maintain position. According to analysts, the energy expended would be equivalent to 6 years' worth of station-keeping fuel, suggesting a transfer of a significant amount of propellant from Shijian-25 to Shijian-21. This kind of refueling could unlock long-term orbital missions previously constrained by fuel limits. The implications of this maneuver extend well beyond Earth's immediate neighborhood. Orbital refueling is considered a crucial technology for sustainable deep space exploration, including missions to the Moon and Mars. By refueling satellites in high orbit, China can send heavier payloads deeper into space, reduce reliance on Earth-based resupply, and extend the functional life of spacecraft. This development comes shortly after China's Chang'e 6 mission returned samples from the far side of the Moon, a feat no other country has accomplished. During the same Senate hearing, former NASA Administrator Jim Bridenstine issued a rare and blunt warning, stating that the U.S. may not land astronauts on the Moon before China does. That admission marks a significant shift in tone from U.S. leadership, which has traditionally viewed NASA's Artemis program as the leading candidate for a return to lunar soil. If China can now conduct large-scale orbital maneuvers and refueling, it may leapfrog over current U.S. limitations, especially those tied to launch delays, crew vehicle readiness, and infrastructure development. Beyond lunar ambitions, the successful docking and fuel transfer signal that China is mastering autonomous orbital servicing, a complex set of capabilities critical for future space dominance. Docking in geosynchronous orbit is extremely difficult, given the vast distances, exposure to radiation, and delicate timing needed for precision control. China's apparent success points to the possibility of in-orbit satellite repair, debris removal, and spacecraft assembly, technology still in development or theory for most other space programs. The Shijian satellites have long been part of China's experimental fleet, and this mission confirms they are now performing advanced operations beyond passive observation or basic research. Such capacity could eventually allow China to build permanent orbital infrastructure, including space stations, lunar gateways, or fuel depots, giving it a strong advantage in the coming era of cislunar economics. The U.S. response has been pointed and immediate. The Senate hearing, titled, "There's a Bad Moon on the Rise: Why Congress and NASA Must Thwart China in the Space Race," reflected mounting concern in Washington about America's slipping leadership in space. Former U.S. space officials stressed that China is advancing faster than previously believed, not only in scientific milestones but also in strategic autonomy. The Artemis program, despite its ambition, continues to face delays in launch schedules, hardware readiness, and budget constraints. These delays could give China the window it needs to send a crewed mission to the Moon before any U.S. astronaut sets foot on the lunar surface again. Bridenstine emphasized that Congress must act decisively to fund and accelerate American space projects, particularly those involving in-orbit refueling, autonomous spacecraft operations, and lunar surface readiness. Without matching China's pace, the U.S. may soon find itself responding to breakthroughs rather than setting the pace.